Hello, everyone. We are going to go through those orbital diagrams that we discussed in class, just in case you missed anything. So let's remember that we started off our whole discussion on electron configurations based on our principal energy levels. And remember, that's the most general arrangement of electrons, just knowing how many are in the first shell, how many are in the second shell, and so on. In our previous lesson, we worked on our sublevel electron configurations, which gives us a little bit more information, such as the 3 electrons that are in our first energy or our second energy level. Those get further broken down into the 2s and 2p sublevels, and it shows us how many electrons are in each. Today, we're going to take it one step further and look at how those orbital diagrams then get broken down into their orbitals. So while 1s and 2s seem pretty similar, when we look at 2p, we'll be able to look at which orbital within 2p are filled, half filled, or empty. So just a couple little things. Remember that type of sublevel refers to the shape, and it also corresponds to the number of orbitals. So S always has 1, P has 3 is what you've seen so far. Each orbital can only hold a maximum of 2 electrons. You saw that in the POGL, and we'll go over the principle that goes with that. So if you look at the key that's on Classroom, you'll see this in color, which will show you a little bit more detail of what these shapes look like. But for our S sublevel, there is 1 orbital within it, which allows it to hold its 2 electrons. In our P sublevel, there's 3 orbitals, which means for each one that can hold 2, it can hold up to 6 electrons. And that should be familiar again from when we did our electron configurations. D has 5 different orbitals, with each having up to 2, we can hold 10 electrons. F is 7 orbitals, which allows it to hold up to 14. So a little bit with like terminology. So our orbitals, usually we're going to use lines when we're drawing them, but you could also see them in boxes. One little thing is like if we look at P, this one line represents the orbital. This whole set here would represent the sublevel for P. And then if we were to look at 3s, 3p, and 3d, this could potentially represent all of the third energy level. So make sure you're keeping that terminology straight just in terms of questions, especially multiple choice questions that can catch students. All right, so what you saw in the POGL were these 3 principles illustrated for you. So the off-ball principle is one where the electrons occupy orbitals of the lowest energy possible. So that would be filling 1s, followed by 2s, and 2p, and 3s, and so on. Keeping track of those exceptions like filling 4s before 3d because 4s is in the lowest energy available. So this is referred to as the buildup principle. Hund's rule has to do with when filling orbitals other than s, because s only has 1, electrons are going to be placed in those individual orbitals before they pair up. Remember, electrons are negative particles, and like charges like to repel. So if we're trying to put them into the same orbital, they're going to be occupying the same space. So if we can put them into different orbitals, which go around the nucleus in different directions, that will decrease that repulsion and decrease the energy, which is favorable. So just remember, especially in P, D, and F, to put them in individual orbitals first, then you can pair them up. The Pauli exclusion principle is just that there's no more than 2 electrons that can be in an orbital, and if they are in the same orbital, they have to be paired. So make sure you can pause the video if you need to get those definitions down. I would put a big star next to this. This is something that sometimes students overlook when they're studying, and you can catch them on questions such as this next one here. So this one is looking for, well, what's getting violated in each of these orbital diagrams? So if we look through at this first one, we are going to see that we have these 2 electrons in the same orbital. And while they have opposite spins and they're both in 2p, we know that from Hund's rule, they need to be in individual orbitals. So this would be Hund's rule, okay, that they should be in individual orbitals. Okay, if you take a look at the next one. Now this would of course have to be stated that this was in the ground state, because you could have this configuration for an excited state. But if we're talking about a regular ground state configuration, 3s is empty while 3p was getting filled up. So that is a problem because we know that due to the off-ball principle, 3s should be filling first because it's a lower energy than 3p. So this one would be a violation of the off-ball principle. Okay, and that would be the lowest energy first. All right, and then finally, when we look at C, we are going to be looking at how, yes, okay, everything looks like it's being filled up correctly. We don't have any issues with individual orbitals, but we do see that there's an issue here with 3s where the electrons are spinning in the same direction. So that would be a violation of the Pauli exclusion principle. And the idea that they have to have opposite spins. All right, so get very familiar with those and also help you when we go to draw these orbital diagrams. All right, so let's do some practice. You're going to want to have your periodic table nearby, which I'm going to get as well. All right, so if we go to take a look at these, first we have fluorine. So this is going to be very similar to our electron configuration. So here I'm going to look at fluorine. I can see that it's going to end up in 2p. It's in the p block, the second level, and I have those 9 total electrons. So with this, I'm going to go ahead and I'm going to have my 1s, 2s, and then p has to have 3. Okay, I know I'm going to end up in 2p, so I'm going to have my first and second, third, and fourth electrons. That means I have 5 electrons left, which I can also tell if I pull out this one from our last video. Here's fluorine right here, so I know it's going to be 2p5, which makes sense. I have 5 electrons left, so I'm going to fill them in as 1, 2, 3, 4, 5. All right, if we look at phosphorus, and phosphorus is capital P right here, it is in the 3rd row in the P block, so this should end up in 3p3. All right, so let's go ahead and write the orbital diagram for phosphorus. So I'm going to have my 1s, 2s, 2p, 3s, and then as we said, it is in the 3rd row, P block, so this is my 3p. So I know until I get to 3p that these are all going to be filled completely. Okay, now I have 3 electrons in 3p, and this is where we need to make sure that we're following Hund's rule. So those 3 have to go into individual orbitals, and I happen to have them all spinning up. Okay, so that would be our phosphorus one. All right, as we move on to iron and tin, which have more electrons, I am going to do the noble gas abbreviation or the condensed abbreviation with this one. So for iron, which is in our 4th row, but this is going to be a part of 3D, I'm going to use argon, which is the noble gas that comes before it in the 3rd row. So for this, I'm going to have my argon, which represents everything through 3p. So then my next one is going to be 4s. And then, as I said, iron exists in that D block, which would be 3D. So this is going to be 3D here. So I know 2 electrons are going to be in 4s. So argon is 18 electrons. 4s gives me 2 more for 20. And iron then has 26 electrons. So I have 6 more electrons to go. So then that means that I'm going to start with my first 5 in my individual orbitals. Here's my first 5. And then my 6th electron in 3D is going to be spinning down and paired up in the first orbital. So that would be the correct orbital diagram for iron in this case. If I take a look at this last one, which is tin, tin is Sn. This is in the 5th row P block, so this is going to end up in 5p2. Especially for this one, I'm going to definitely use the condensed abbreviation with krypton, because krypton is going to cover the first 36 electrons, everything through 4p. So when I go to start filling after that, I'm going to be starting in my 5s, then I'm going to have 4d, and then I'll be 5p. So like I said, I'm going to use krypton here, and then I'm going to have 5s, and then I'm going to have 4d. So I'm going to draw out my 5 orbitals for 4d. I try to make them distinct from the other neighboring sublevels. And then, like I said before, the next one is going to be 5p. So I know up until 5p that everything's going to be filled. So I can go ahead and fill in those electrons. And then I get to 5p. And again, we had 2 electrons that were going to be existing in 5p. So following Hund's rule, we're going to put them in our individual orbitals. Okay, so this is really just building on our electron configurations. We're just showing how they exist in our orbitals, which just gives us a little bit more detail about our electrons.